Hello, everybody. You are welcome to the to clip 4 of part 2 digital communication in the course of modern wireless communication and applications. Now we come to the part of probability of error. We mentioned the previous clips that due to the channel noise and fading, so the received signal will be like noisy, and also it is power will be like very low due to the propagation, and because of that, there is a possibility or probability that the symbol will be incorrectly detected. It means that the receiver will detect the symbol as not the one which was transmitted. So then we have probability of error. Okay, and we mentioned also that the quality of the received signal is could be measured with the signal to noise ratio, and the signal noise ratio is the we mean the average signal power to the average noise power. There is mapping of it is possible in digital communication to derive the some equations, some closed form equations, to determine the probability of error based on the signal to noise ratio. These functions depends on different factors. For example, the digital communication method, like is it amplitude shifting or FSK or BSK or QAM. Depends also on the number of symbols, depends on the detection method applied in the receiver, for example, coherent detection or non-coherent detection, and so on, and also depends on the channel model. So the simplest channel model that we can use is the additive white noise channel. It means that the received signal, when we say additive white noise channel, we mean that the received signal, as actually we saw it in the previous clip, that R of t equal to the transmitted symbol, for example, is I of t plus noise. So this is called additive white noise channel. So this is the simplest form of the channel that we can deal with, and most of the basic functions that state the probability of error is based on this form. Of course, in reality, that or in more realistic scenario, that the received signal could be represented like some alpha, actually alpha t times si of t plus n of t, and this alpha t also will like a productive noise, so it will introduce also some problems in the detection process, and this is due to the for example, the fading of the channel. Actually, considering this fading and other problems of the channel, it can also like modify somehow the equations that we use to calculate the probability of error. We are not going to details of such computation. We just want to give some general introduction, some general concept about the calculations of the probability of error. Just to give impression about the signal noise ratio, assume here that we have transmitter, and the transmitter here is the distance between the transmitter and the receiver is about 100 meter, and also we want to use the two rays model that it was given in the previous part, in part 1. So and the noise average noise power at the receiver part was given as minus 50 dBm, and the requirement here is to calculate the signal to noise ratio. So the average received power, as it was given from the previous part, is the transmitted power times the gain of the transmitting antenna times the gain of the receiver antenna times the height of the transmitting antenna square, height of the receiving antenna square, divided by distance of the power 4. Those values are given in this example, so we just substitute them here, and then we received that the power is 35.6 microwatt. Okay, And then the signal to noise ratio is the received average received power, 35.6 microwatt, divided by the noise power, which is given as minus 50 dBm. dBm means that dB related to the milliwatt, which means that 10 of the power minus 8. And with this calculation, we got this is the signal to noise ratio is 3600 or 35.5 dB. Okay. Of course, now with this SNR, if the modulation technique, for example, is binary phase shift keying, we can use this value to calculate the probability of error, transmission error in this situation. However, there is one important part or important point here, that the SNR is not always good measure for the communication quality. This is a big problem. Why? Okay, now if let me explain this over the blank um, screen. Okay, and maybe I will take this down. Yes. So we mentioned before about the that we might have binary phase. Sorry, binary phase shift keying, or for example, 8 array phase shift keying. Okay. Now, in binary phase shift keying and 8 array phase shift keying, if we compute or if we represent the formula for both cases, it will be like that. For example, it is y of t equal to a0 cosine 2 by f0 t plus phi. If this is the symbol I, then we can put here phi I. Of course, it will be also of t. Yeah. Now, the average power, the average normalized power for this signal will be A0 squared divided by 2. This is the average power. Okay. And for phi I of t, for binary or for 8 array phase shift keying or 16 array phase shift keying or whatever changes of the phase, the power is still the same. So the average power is the same. So now in the binary phase shift keying, we send only two phases like this one and this one. But in 8 array, we will send something like that. So we have phase here and phase here. So we can transmit different phases where each phase represent 3 bits instead of 1 bit, like in this case. It is clearly or it is clear for everyone to see that the 8 array phase shift keying, if we transmit with the same power, the probability of error will be higher. The probability of error in this case will be higher than the case of binary phase shift keying. So the probability of error, for example, for 8 array will be greater than the probability of error in case of binary phase shift keying, given that the same power, if we use same power and also same channel condition. So it will be the probability of error will be worse in case of 8 array phase shift keying, because the distance or the separation between different symbols becomes closer to each other and the probability of error will be higher. Okay, but the signal to noise ratio, normal signal to noise ratio, is the received power divided by noise. So the received power, which is the transmitted power multiplied by, for example, the channel gain, it will not reflect the impact of the distance between these, for example, between the smaller like distance between symbols. Because of that, SNR is not good measure to represent the probability of error in case of uh, in case of digital communication in general. If you want to use only binary phase shift keying, it will be okay. But if you want to use more efficient like modulation, like higher MRA BSK or like QAM, then the SNR directly is not suitable for that purpose. Okay, so we need actually to have some simple modification for this SNR to be able to be used in the calculations of the probability of errors in digital communication. Okay, so now we can see what we do. So actually, in digital communication, it is more often to use EB over N0. So EB, we calculate the energy per bit. Okay, so the energy per bit is the average received power times the bit duration. Okay, and divided by the noise spectral density, because now we have energy, so energy should be divided by energy, not by power, to keep this as unitless like measure. So we divide the energy per bit by the noise energy or the noise spectral density. Okay, and this could be done like in this way. So eb over n0, the energy per bit, divided by n0. The energy per bit is what? Is the received power times the bit duration divided by n0. N0 is the noise power divided by the system bandwidth, or the noise bandwidth, or the useful bandwidth in the system. Okay, so this could be done in this way. So BR divided by N, what is this? This is nothing but the SNR actually. This is the signal to noise ratio that we know, the received power divided by the noise power. But now it is multiplied by another factor, very important factor in digital communication, which is the system bandwidth. This is the system bandwidth divided by the bit rate. The system bandwidth divided by the bit rate. This is very important. In case that the system bandwidth is the same as the bitrate, then EB over N0 is the same as the SNR. But generally it is not. Actually, this one it can be represented like SNR, okay, and multiplied by BW, the system bandwidth divided by RB, or it can be divided by RB divided by the system bandwidth. It is the same. Okay, what is this? What is the bit rate divided by the available or used bandwidth? We talked about this before, if you remember. This is called the spectrum efficiency. The spectrum efficiency. We said that, for example, in binary phase shift keying, we might have 1 bit per second per hertz. Okay, so in binary phase shift keying, it is EB over N0 is the same as SNR. Okay, in case that the bandwidth is the same as the bit rate. Okay, and now if you use higher modulation, if we use higher modulation, so we got higher efficiency or spectrum efficiency. For example, if we have higher efficiency such that we have system with 10 bit per second per hertz. What it means? It means that in each hertz we send a rate of data rate of 10 bits per second in each hertz. Okay, so how this efficiency will be reflected into EB over N0? Of course, the EB over 0 will be lower because this is the SNR. Now SNR divided by 10. SNR divided by 10. So it means that SNR will be reduced because of the increasing the efficient spectrum efficiency. So remember this compromise between the EB over zero, which means that the transmission equality in terms of probability of error and the spectrum efficiency. As you increase the spectrum efficiency, you will lose the performance or the reliability of the communication link because the probability of error will be higher and higher. So this is actually very important lesson in digital communication. Usually what we are doing in reality or in practice, once we have very high SNR, it means that the channel is excellent, then we can exploit this case by increasing the spectrum efficiency. So we can increase the number of bits per second per hertz once the SNR is very high. But if SNR is small, then what we do, we reduce the transmitted bits per hertz, per second per hertz. So this is the way that we are doing. So the spectrum efficiency can be increased once we have very high SNR, and it can be or should be reduced in case that we have low SNR in order to keep the reliability, or in order to keep the probability of error for the symbols as small as possible. uh, what is the required probability of error? It depends on the application. Depends on the application. For some applications that we need very low probability of error for the symbols, for the other applications we might like relax that condition. For example, in voice communication, in voice communication, if the simple error even high as like 1 per 1,000, so if one packet per 1,000 packet was not received correctly, or even more like 10,000 per 1,000 packets, so which means that 1% of the packets were not received, still we can manage that. We can listen to the speech or to the voice. Somehow, of course, we can notice some like degradation in the quality, but still it works. But for also in video communication, for example, if we have like one frame missed, so still we can manage it. Maybe we can notice that we have some degradation in the quality, but still it works. However, in some other applications, we don't allow any error. For example, if you want to make a bank transaction over the internet, so you don't want that you write like 5 and it is received like 20, for example. So in that case, we need to have like some check and retransmission in case of errors. So we can allow some errors in some applications, but it is not allowed for other applications. It depends on the application itself. Okay, now let us talk a little bit about noise. Uh, we mentioned in the previous clips that we have two kinds of noise in telecommunication. We have thermal noise and we have shot noise. We talked about both of them a little bit. Now we just try to formulate the thermal noise in terms of mathematics. So the average noise power in thermal noise is given by Boltzmann constant times the system bandwidth, times this TE is called the effective noise temperature. If we talk about one resistor or one conductor, this TE can be also the physical temperature. But when we talk about system, then we talk about the equivalent noise temperature. Okay, and this Boltzmann constant is known as 1.38 times 10 of the power minus 23 joule per Kelvin, and BW as the system bandwidth. And as we said, TE is the effective noise temperature, and it is given also in Kelvin. Okay, so what is the noise spectral density? Noise spectral density is the noise, because this n is given in watt, so it is watt per hertz, or actually it is in joules. So it is the equivalent to the noise like energy. Okay, so n0 is called noise spectral density by dividing n the average noise power by the system bandwidth. So when you divide system bandwidth, this one will be removed, and then what we get is k, the Boltzmann constant, times the effective noise temperature. Okay, so this k, or the Boltzmann constant, is a constant, so it is always fixed. So actually, the noise packet density depends always on the effective noise temperature of the system. Okay, and we call this noise actually white noise, and it is white noise because it is Bose spectral density is flat over all useful frequencies in communication, as we show it here in the figure. So it is from minus infinity up to infinity. Actually, it is not infinity because we don't have like infinity frequency, but for the whole range of useful range, actually, of wireless communication, up to maybe 2 or 300 gigahertz, that this spectrum is very well like modeled like flat, like it is shown here. Okay, this is the double-sided noise, and if it is one-sided noise, it means that frequency from 0 to infinity, it can be directly as n0. Okay. As a common factor that usually we use for general noise that we don't know, sometimes we can model it as ambient temperature, that T0 equal to 290, and this is the same that we usually use as a reference, so this is called T0, and we use it for antenna, for example, if we want to take like some value, it is T0. Of course we can take sometimes this 290 can underestimate the noise level at the antenna. If you have system, for example, the antenna is connected to your, for example, mobile phone, and inside your mobile phone we have blocks inside. So we have, for example, the first thing after the antenna, maybe we have the low noise block, is called low noise block or low noise amplifier, and after that we have, for example, modulator or down converter, and after that we have amplifier. We have many systems inside. Okay, so if we want to see that this is the system, this is the communication system, the receiver, this is the receiver. Okay, so the composite noise temperature consists of the input temperature. Remember, temperature here means the noise, thermal noise. This is what we mean. Okay, because just you need to multiply it by the Boltzmann constant, then you will get the noise spectral density. So this is the input noise from the antenna, for example, and plus the first block in your communication receiver is given as it is T1, the temperature. For T2, T2 is divided by the gain of the first block, and T3 is divided by the gains of first block and second block, and so on. Based on that, it is extremely important in designing very good receiver to take care about the first amplifier. The first amplifier in the system must be designed to be low noise and high gain. So when it is low noise, it means that T1 is very small, and since it is high gain, then the noise of other systems will be divided by the gain of the first block. Of course, this will give you the equivalent noise temperature here at the input. So the equivalent noise temperature of the system here will be T1 plus T2 divided by J1 plus and so on. If we keep this T of the system, of the communication system, as a small value, what it means? It means that the sensitivity of this system is high, so it is able to detect even very small signals. But if the noise is high, if this T is large, then the sensitivity of the system is low, and your system cannot sometimes detect the signals. So it is very important to keep the noise temperature of the first of this system as low as possible, and then by we can do that by special design for the low noise amplifier or low noise block. There's difference. Low noise amplifier usually is consisting only of like amplifier which is designed to be low noise. And when we say low noise block, it means that it has two things: the low noise amplifier and also the down converter, that it can reduce the frequency to the medium frequency. Okay. Now we have already seen that the signal to noise ratio or the performance is represented by EB over N0, and we saw the relation between EB over N0 and the signal to noise ratio. Without going into the derivations, usually we give these derivations in other detailed, like master courses, like digital communication, for example. We go through deep analysis and deep derivations for these equations. But now, in this course, I want to give you impression about how it looks like. The probability of error for binary phase shift keying is usually given as in this equation. So the probability of error per bit is Q. Q here is called Q function. The Q function is derived from Gaussian distribution, and it is given in this shape. So you can find it from tables, or you can also find it if you have tables of error function or complementary error function. You can use it. It is related to the complementary error function for those who like know the Gaussian and the error function and the complementary error function. It is widely used in statistics anyhow. So this is the Q function that we can compute the probability of error in case of PSK. In case of FSK, orthogonal FSK, this is the probability of error. It is quite similar, but here we have 2, and here we don't have this. 2 actually, this represents the distance between the symbols. As if you remember from the previous clip when we said that the distance in binary phase shift keying is larger than the distance in case of orthogonal system like in the frequency shift keying, and because of the difference in distance, this causing this causes the probability of error in case of binary phase shift keying to be better than the probability of error in case of the orthogonal system like FSK. You can see here the difference between them. So here the if I asked you which one you think for the binary phase shift keying and which one you think about the orthogonal frequency shift keying. Yes, the blue one is better. The blue Y. For example, when EB over N0 equal to, let's say, 5 dB, if you take for 5 dB, you can see that the probability of error in this case is about maybe 7 times 10 of the power minus 3, but it is worse in the orthogonal system. As you can see, it is about zero point 0.7. So there is a difference between them. So the blue one is better than the red one. The blue one is for the binary phase shift keying, and the red one for the some orthogonal other orthogonal like FSK or ASK. If we went to the like M array, general M array modulation, like for example M array PSK or M array QAM, for example, we can see this is the probability of symbol error. The probability of symbol here, the probability of error per symbol, not per bit. If the probability of error per symbol is very small, then the probability of error per bit, we can assume that they are like distributed evenly, so we divide them by the number of bits if bs is very small. Okay, and anyhow, the probability of symbol error is equal to 2 q function also, and now we have 2 es means that it is the energy per symbol. To get the energy per bit, simply you just multiply es equal to eb times the number of bits per symbol, because m, it is m array. So for example, when we have 6 array b is k, it means that you have 4 bits per symbol. Okay, so m here equal to 16, but log 2 for 16 equal to 4. The number of bits equal to 4. Then the energy per symbol equal to the energy per bit times 4, in this case in the 16 array. But you can see here it is multiplied by sign by over 16, which means that this number is very small number, is a small number, which makes like the EB over 0, or the quality or the probability of error will be increasing in this case because of this M array. As we increase M, as the probability of symbol error will be increased. So we saw already that these equations actually they are like in the practice they underestimate the realistic probability of error, because the probability of error is even more worse than what we got from these equations, because in these equations we ignore the impact of like channel fading, for example. We take into account only the noise, the additive noise. Okay, and but in reality we have other kinds of problems. Of course we can take care about them also, or we can derive the probability of error in case of fading, for example, because this fading will introduce some like random process, or a stochastic process for the ES, for example. The received energy will not be fixed anymore. The average will be also will follow the fading in this case. If we didn't mitigate the fading by using some advanced techniques, then ES will be also like random variable in or random process in that case. And in that case, the probability of per symbol or the probability, sorry, or the probability per bit error actually will be itself a random variable. In this case, it will not be fixed, but will be a random variable. And in that case, we need to averaging over this PE over the probability density function of this probability of error. This could be a little bit complicated for non um, like math course like this one, so we don't want to go into the math, but just keep this in mind that these equations are actually not the realistic equations in practice, but it is it is underestimate the actual errors. Okay, because of that, we need or it is very important to use the coding. Coding is very, very important, especially channel coding. The channel coding is useful because we can, if error happen, then we can detect the error, and also in the forward error correction, we can also correct the error at the receiver side. Before we go to the coding, if, especially for the in the next clip, so I just we take a survey about kinds of coding available. So if, generally in telecommunication, when we say coding, we might mean that cryptography, source coding, error control coding, line coding. So cryptography, we know that it is for example, for security, to increase security for the transmission for data, and to make also the link confidential. And there are many techniques to keep or the security of communication link, and source coding, for example, to compress data. Okay, it is very important also in many applications, for example in video application, for in big, for example, transmission. So or coding, actually we can see here the data rate of video could be reduced to be 1% of the average or the actual data rate. For example, if the actual data rate 100 megabit per second, with this MBIG, if we just accept some degradation in the quality, we can reduce this up to like 1 or 2 up to 3 megabit per second by using this compression techniques. We have very powerful compression techniques that we can reduce the data rate of voice of mainly for video signals. And line coding is to improve that spectral characteristics, for example, reducing the DC value or the average value if it is not zero. And actually, the most important part that we want to discuss in the coming clips is the error control coding. Error control coding is to increase the robustness of the transmission of data. And we have two kinds. We have forward error correction, FEC, and we have error detection and retransmission. In the error detection and retransmission, we don't need to implement algorithms to correct the error, but once there is error, then the receiver will send to the transmitter and asking to retransmit the packet again, so that it will be retransmitted until it is received like correctly. So in the receiver, they have the capability to detect if error happen. Of course, it has also some limit for that. So in the coming clip, we will talk more about error control coding and the kinds of error control coding. See you then. Thank you.